Hello everyone, so today we're going to talk about inflection points. But before we get started with that, we first just want to recall these 4 statements that are important. Okay, so the first part is just saying that if the second derivative is positive, then the first derivative is increasing. And if the second derivative is negative, then the first derivative is decreasing. Okay, and then we also had that if the second derivative is positive, then f is concave up. And if the second derivative is negative, then f is concave down. Okay, so now you're just wondering what even is an inflection point, right? So here I define for you an inflection point. I'm saying suppose a function f is continuous at x equals a. If f changes concavity at x equals a, then we say that a comma f of a is an inflection point of f. Okay, so the specific ordered pair in this case we consider an inflection point. So looking at this visual, hopefully you guys can see that at x equals a, I'm switching from concave up to concave down. Because when you look at it, right, to the left of x equals a, we can see that it's bending upward. And then to the right of x equals a, we can see that the graph is bending downward. So it definitely is changing concavity. Also, what you have here with this visual is I'm showing you with these tangent lines here, looking at the tangent lines in orange, we can see that the slope of the tangent line at each of these points is increasing. So hopefully you can see that the slope there is increasing. And so since the first derivative at each of these points is increasing, then I know the second derivative is positive, and so that tells me that the function is concave up. Okay, so I'm sort of showing you visually why all of these statements that we said in the beginning up here make sense, because visually I'm showing you this part, that if the first derivative is increasing, then the second derivative is positive, or if the second derivative is positive, then the function f prime of x is increasing. Okay, so you can see that visually here, because looking at these slopes, I go from negative to 0 to positive, so reading from left to right, my slopes are definitely increasing. Okay, and then looking to the right, we can see that these slopes are decreasing. Okay, so you can see there that the second derivative is going to be negative, and therefore the function will be concave down. So of course we can see visually that the graph is bended upward to the left to x equals a, so it's concave up, and to the right it's bended downward, so it's concave down. But what if I just gave you the function and I said determine the inflection points, right? That's where we're going to need these statements that I told you in the beginning. Okay, so here's my big question. How do we find inflection points of a function f algebraically? Well, here I'm saying that we say a point x equals a satisfying the second derivative at a is equal to 0, or the second derivative at a is undefined, is a candidate for an inflection point. So this does not necessarily mean that x equals a is an actual location of an inflection point. To determine whether x equals a is a location of an inflection point, we need to check whether the second derivative changes sign at x equals a. So if it does change sign at x equals a, then x equals a is a location for an inflection point. However, if it does not change sign at x equals a, then x equals a is not the location for an inflection point. So now let's just actually look at an example. So it says find the inflection points of the function g of x equals x cubed minus 9x squared minus 48x plus 52. So the first thing I want to do is find all possible candidates of inflection points. So in other words, I need to find the second derivative, set it equal to 0, and solve for x. And then I also need to check for those points where the second derivative is undefined. Okay. So let's just first compute the first derivative. So I get 3x squared minus 18x minus 48. And then computing the second derivative now, I'm just taking the derivative of the first derivative, so I get 6x minus 18. And so now I'm going to set this equal to 0, and then solve for x. Sorry, minus 18 equals 0. So here I get 6x is equal to 18, which implies that x is equal to 3. Okay, so here's my possible candidate. And also just note that the second derivative, the domain is all real numbers because it's a line. So any x value I plug into 6x minus 18, I'm going to get an output value. So it's not going to be undefined anywhere. Okay, so these are the only possible candidates. It's just x equals 3. Now what I'm going to do is I'm going to make a number line just like I did with the first derivative test, but then I'm going to plug in values to the left and to the right of 3 into the second derivative because I want to see if it's positive or negative to the left or to the right of 3. Okay, so I'm going to make my number line. So I have negative infinity to 3 and then 3 to infinity, and so I'm going to just pick a number that's to the left of 3, so I'm going to pick 0. And then to the right of 3, I'm going to pick 4. And remember, I'm plugging it into the second derivative because I want to figure out if the second derivative changes sign at x equals 3. In other words, does it change concavity? Okay, so 6 times 0 minus 18. This is definitely less than 0. So this is going to be negative. And then 6 times 4 minus 18. That's definitely going to be a positive number, so it's going to be positive. So since I changed sign, right, at x equals 3, this is an inflection point. And in particular, just note that, that f is concave down. Okay, just note that means concave down. And then f is concave up. Okay, so I'm going to write here concave up and concave down so that you can see how to identify the intervals here for concavity, but it's not going to be too hard. So at x equals 3, we don't include it in either being concave up or concave down, so it would be considered neither. So for concave down in this case, it's going to go from negative infinity to 3, but not including, so you should have a parenthesis there, not a bracket. And then from 3 to infinity for concave up. Okay, and so I'm going to say here that there is an inflection point at x equals 3. Okay, so I'm only giving the location for the inflection point here. All right, so some of you, it seems that you may or may not have forgotten to find local max and minimums or global max and min. Make sure that you are plugging in that x value back into the original function to find the corresponding y value. Okay, because if you just say at x equals something, you're just giving the location, you're not giving the full, you're not giving the local extrema. So similarly in this case, if I want to know the coordinate of the inflection point, not just the location, then I need to plug 3 back into the original function, and then I will have my inflection point. Okay. So f of 3 is equal to, and now going back up here, we have that this is going to be 3 cubed minus 9 times 3 squared. And then we have that this is minus 48 times 3, and then plus 52. Okay, so this is going to be 27 minus 81, and then minus, this is going to be 48 times 3, so minus 144 plus 52, and so this is going to give me, let's see, minus 144 and then plus 52, so this is going to give me negative 146. So my inflection point is 3 comma negative 146.